Okay. Section 14.3, partial derivatives. So before I start to talk about partial derivatives, let me just say that the derivative of a function of several variables is not a partial derivative. However, once we define a derivative of a function of several variables, or maybe several functions of several variables, it will involve partial derivatives. Step, we'll be looking at partial derivatives, and these will be very similar to ordinary derivatives, where I just treat one of the variables as being fixed, as well as all of the variables except for one is being fixed, and I only vary one of the variables. And so, partial derivatives. Let's use this curly D notation. For this will be Leibniz notation, which looks similar to Leibniz notation, but instead of using a regular D, we'll use this curly D. So the partial, so curly df, curly dx at AB, the first partial of f with respect to x at AB is defined as the limit as h approaches 0 of f at a plus h comma b. So notice that only the x coordinate here is varying, minus f of a b all divided by h. Curly f curly y at ab is limit as k approaches 0, f of a comma b plus k minus f of ab over k. So only the y is varying. Okay, so let me look at some notation. So popular notations. I can use a subscript. Say if I want to look at the partial of f with respect to x, I can use the subscript of x or subscript of 1 because it's the first variable. I can use the curly d notation, curly df over curly dx. Sometimes we let z equal f of x, y, and we use this notation, curly dz over curly dx. I don't really like that, but sometimes I use it because if you have a function of 3 variables or so, then usually I use z for the third variable. So then this gets confusing. You can also use the d1 or x. Same for y. Use a subscript of y to denote the partial of f with respect to y. Use the curly d notation. Use the curly d notation with the letter z denoting f of x, y. Use a subscript of either y or 2. Use the d notation with a subscript of either y or 2. So those are the first partials for a function of 2 variables. Let's look at the second partials. The second partial derivative of f with respect to x. And so use the curly d notation. It's the same notation for Leibniz that we used in calculus 1. It's just the partial of f with respect to x, and you take the partial of that with respect to x. You can use a subscript of xx, 1, 1, and you can use z as equaling f of x, y. Same for the second partial of f with respect to y. Use the subscript of yy, 2, 2. You can again use the d notation. I don't know why I didn't write it, but the mixed partials. And so the partial derivative of f with respect to x, and then to take the partial derivative of that with respect to y, you can use the subscript notation, xy, 1, 2, or Leibniz notation. But in Leibniz notation, it goes in the opposite direction. So if you take the second derivative of f with respect to x and then to y, it's curly d squared f over curly dy curly dx. And again, you can let f of x, y equals z. And so the partial of f with respect to y, followed by the partial of partial of that with respect to x, is denoted by a subscript of yx, or a subscript of 2, 1, or curly df over curly dx curly dy. Okay, so let E denote the standard basis for Rn. And so it's equal to a vector having components of 0 everywhere except it has a 1 in the ith component. Then I can define, oh, this is a sub I. That's an I there. So I can define, there, that's an I, the partial of f with respect to x sub I for any function of several variables. So not just the 2 variables, let's say n variables. And so curly d f over curly d x sub I is equal to the limit as h approaches 0 of f evaluated at x plus h e sub I. So only the ith component is varying minus f of x over h. So that's an extension of that works for any dimension, as long as you have a function going from R to Rn. So this is some function f going from R to Rn. Okay. So many times the mixed partials are the same. So let me give you Clairaut's theorem. So Clairaut's theorem says that if a function of 2 variables is defined, there it is, finally. Suppose f is a function of 2 variables, and it's defined on that both the partial of f with respect to xy and the partial of f with respect to yx are continuous on this neighborhood of the point AB, then the mixed partials are equal to each other. And so long as the mixed partials are continuous in some neighborhood of a point, then they will be equal to each other. In later today, I will give you an example where this is not true. So you have to have that it is continuous in a neighborhood. Otherwise, these mixed partials will not be equal. Let me do on page 964, problem number 16. In exercises 15 through 40, find the first partial derivatives of the function. So problem number 16, f of xy is equal to x squared y minus 3y to the 4th. So let's take the partial of f with respect to x. And so when I take the partial, I will treat x as varying, and all other things that I see will be treated as constants. So those other variables I'll treat them as a constant. And so the derivative of x squared is 2x times the constant y. The derivative of the constant, negative 3y to the fourth, is 0. So that's my first partial with respect to x. Let's take the partial of f with respect to y. And so the derivative of the constant x squared times y is just the constant x squared. The derivative of 3y to the fourth is 12y cubed. And that is the partial of f with respect to y. Okay, let's do problem number 20. Suppose z is equal to x sine xy. And so let's take the partial with respect to x. So let's use the product rule. Derivative of the first times the second plus the first times the derivative of the second. The derivative of sine is cosine, evaluated at the inside, times the derivative of what's inside. And so the derivative of x times the constant y is the constant y. And that is your answer. Let's do the partial with respect to z. So the derivative of the constant x is 1. It's just x. The derivative of sine is cosine. The derivative of the constant x times y is just the constant x. And so I get x squared. And that is your answer. So let me write this as, again, you could remember the derivative, but it's probably best to write this as e to the y ln x, just to remember things. Okay, so let's take the partial with respect to x. Well, first off, y is a constant. And so the derivative of x to a constant is just that constant times x to the power of 1 less. So that's your answer. Second, let's take the partial with respect to y. Well, the derivative of e to the y times the constant ln x is just the constant ln x times, it's e to the exponent. And let's just rewrite that as x to the y times the derivative of the exponent. Well, y times the constant ln x, the derivative of that will just be ln x. So I'm done. 30. Let's take the partial with respect to alpha. Well, let's use the fundamental theorem of calculus. So the derivative of the antiderivative, or whatever you want to call this, is just the integrand. Or, well, where I'm treating x here is, treating alpha here as my variable. So, well, since alpha is a lower limit, we recall that this is just minus the integrand evaluated at alpha. Whereas, if it's the upper limit, we just evaluate at the integrand. Let's take the partials. So the partial with respect to x so it's x times a constant. And maybe I'm going to do this. I need more space. So it'll just be x to a constant is, well, bring the constant down, times, well, that variable x to the power of 1 less. And that is your answer. Okay. Maybe let's put the z over here to make it look nicer. Okay. Yeah, that looks nicer. Okay, let's do the partial of, don't say you're, okay, good. Okay, partial of u with respect to y. Okay, so, well, the same thing that we did in this previous problem up here. So I have a constant x to a variable y, which is varying over the constant z. And so the derivative of that is going to equal, well, the same thing, x to the y over z times the derivative of the exponent. Well, times ln x. Okay, just like we had before right here. All times, why do I have an x? Why do I have a z there? Well, this is an x. Okay, x to the power y over z times ln x times the derivative of the variable y over the constant z is, well, 1 over z. And that is your answer. And now let's take the partial with respect to z. So let's take the partial with respect to z. Well, it's going to be the same sort of thing. It's going to be like in the previous one. It's x to the y over z. Trying to get control of my pen. Times ln of x times the derivative of the exponent. Well, the derivative of the exponent, let's give me some more room here. So let's write x to the y over z ln x times the derivative of the exponent. Well, the derivative of the constant y over the variable z is going to be the constant y times, well, this is z to negative 1, so there'll be a minus z to the negative 2. So let's divide by z squared. And that is your answer. In exercises 41 through 44, find the indicated partial derivatives. Okay, so f of xyz equaling x to the yz. Let's take the partial of f with respect to z. So I have a constant x to the power of some constant times the variable z. And so just like the previous, these previous two partials, this is just going to be x to the power yz ln x times the derivative of the exponent. Well, the derivative of the constant y times the variable z is just the constant y. And so let's evaluate this. And so let's evaluate f, partial of f with respect to z at e, 1 and 0. And so plug in 1 for y, 0 for z, and e for x. So 1 times 0 is 0, e to the 0 is 1, times 1 is 1, ln 1 is 1, and so there's just a whole bunch of 1s you're multiplying. So this is equal to 1. And that is your answer. Okay. In exercises 45 through 46, use the definition of partial derivatives as limits. We did use the definition of partial derivatives as limits to find partial of f with respect to x and partial of f with respect to y. Use the limit definition is what they're saying. So let's do that. So the partial of f with respect to x is the limit as, let's do h approaches 0 of, let's just use this, f of x plus hy minus f of xy over h. So that's just the limit definition. And let's do it for this particular case. So this is the limit as h approaches 0 of, replace x by x plus h. Maybe I'll place x by x plus h and keep y. Oh, this is just, it's just x over y squared. And so keep that. Okay. Minus x over x plus y squared all over h. Now, let me get a common denominator to simplify this. So this is the limit as h approaches 0 of x over x plus h plus y squared minus x over x plus y squared. So let's multiply and divide by x plus y squared. The least common denominator is just the multiple of the two denominators. And let's multiply and divide by x plus h plus y squared. Okay, and this is all over h. So this is equal to limit as h approaches 0 of, oh, and maybe I'll just say this. This is the same as, I can then save some space here. Dividing by h is the same as multiplying by its reciprocal. So let me multiply this out. Actually, I might be able to get up here. Save one more space even. Limit as h goes to 0. Let's multiply this out. So this is x squared plus xy squared plus xh plus y squared h minus x squared minus xh minus xy squared over x plus h plus y squared, x plus y squared times 1 over h. And so this is equal to the x squares cancel, the xh's cancel, the x y squares cancel. Wow, so almost everything cancels. So this is equal to h y squared over h x plus h plus y squared x plus y squared. And the h's cancel. Okay. So this is equal to y squared over x plus h plus y squared. I like the way that looks. The limit as h goes to 0 of y squared over x plus h plus y squared x plus y squared. So this term here just goes to x plus y squared. And so this is just equal to y squared over x plus y squared squared. And that's the partial of f with respect to x. Let's do the partial of f with respect to y. It be nearly identical to this. So the partial of f with respect to y limit as k goes to 0, let's say, of f of x y plus k f of x y over k. So this is equal to limit as k goes to 0 of x plus y plus k squared minus x over x plus y squared over k. So let's get a common denominator. X over x plus y plus k squared minus x over x plus y squared. So let's multiply and divide by x plus y squared. And let's multiply and divide the second term here by x plus, let's multiply this out, y squared plus 2yk plus k squared over x plus y plus k squared. And so, all divided by k. And so this is equal to limit as k goes to 0 of x squared plus x y squared minus x squared minus x y squared minus 2xy k minus xk squared over x plus y plus k squared x plus y squared, again dividing by k is multiplying by its reciprocal, 1 over k. So let's cancel. X squares, xy squares. And so I get limit as k approaches 0. Factor out of k, I get a minus 2xy minus kx over k x plus y plus k squared x plus y squared. K's cancel. And so this is the limit as k approaches 0, negative 2xy minus kx x plus y plus k squared, x plus y squared. And so the partial of f with respect to y is equal to as k goes to 0, this term goes to 0, so the numerator is a negative 2xy. As k goes to 0, y plus k goes to y, so this becomes an x plus y squared, and so there will be two of them in the denominator. And that is your answer. Problem number 89. For the ideal gas law of exercise 88, show that T, partial P with respect to T, partial V with respect to T is NR. So I have here that PV equals nRT. That's a universal gas law. That is the ideal gas law. And so I have that, let's take the partial of this with respect to T. And so I have that P. So in this case, let's suppose here that P is only varying with respect to T. And so if I do that, then I have P. Let's just use a subscript for a second. Partial with respect to T is equal to NR. Okay. And so let's multiply by T. So I have here that, let's first, let me first assume that the only thing that varies is P. Let's do that first. And so then I'll have a P sub TV. Okay. So assuming that the only thing that varies in this is the P. Now, let's multiply both sides of my equation. So maybe I should have said that. I take the partial with respect to T. So now let's multiply by T. So I have here that TV partial P with respect to T is equal to nRT. Okay. Next, suppose that nRT. Suppose that I take the partial of this with respect to T. And the only thing that's varying is the V. And so this is P v sub t equals nr. And let's multiply by t. So this is pt, or tp, let's say, partial v with respect to t is nrt. Okay. And so I have the following, that multiplying these two together, that t squared pv partial p with respect to t partial v with respect to t equals nRT squared. But PV equals nRT, so that cancels with one of these. Okay. So I have that t squared partial p partial t partial v partial t is nRT. So cancel one of the t's. So I have the partial of p with respect to t, partial, there's a one t here, partial v with respect to t is equal to nr. And that's what you wanted to show. Okay. So I'm done. Let's do the following. Let's do the following example. Let f of xy equal this piecewise defined function. It's xy over x squared plus y squared if xy is not the origin, and it's 0, y is equal to the origin. Show that the partial of f at the origin is 0. The partial of f of y is at the origin is 0. Yet f of xy is not continuous at the origin. So even though both partials are defined and are equal to each other, they're both equal to 0, still the function is not continuous. And so, you would expect if a derivative in one variable, if a function is differentiable at a point, then you would expect that the function is continuous at that point. Well, notice that if the partials are exist and they're equal at that point, it still may not be that the function is continuous at that point. So that gives you a hint that maybe this is not a derivative. These partials are not derivatives. They're not telling you the whole story. So the fact that if the in the one-dimensional case, if the derivative was 0, well, if the derivative exists, then then the function is continuous. And so since that doesn't work, that gives you a hint that maybe this is not really, the partial derivatives are not really a concept of a derivative. Now, since this function here is defined piecewise, then we must use and since this function is defined piecewise, and since we're taking the partial derivative where it's defined differently at that place I'm trying to take the derivative, so I'm trying to take the derivative at the origin, but it's defined differently at the origin, then I must use the limit definition. Just like if you're trying to take the derivative, well, of a function of one variable and it's piecewise defined, then you really should, and you're trying to take the derivative at some point where it's defined differently, then you really have to use a limit definition to find the derivative. So let's do this. So let's find the partial of f with respect to x at the origin. So this is the limit as h approaches 0 of f of 0 plus h 0 minus f of 0, 0 all over h. So this is the limit as h approaches 0 of f of h 0 minus, well, f is 0, 0, I know that's 0 over h. So let's try to find this. Well, notice that, well, I guess I'll have to go to the next line here. Notice that if you plug in h0 here, I get, maybe I should do one more line down. If you plug in h0, then you get h times 0 over h squared plus 0 squared. I'm assuming h here is not 0 because I'm taking a limit as h approaches 0 all over h. But minus, maybe I'll say minus 0 so it looks nicer. But notice that this is 0. So 0 over 0 0 minus 0 is 0. Well, 0 over h is 0. The limit as h goes to 0, 0 is 0. And that's what you wanted to show. Okay, for the first part. Let's do the second part. The partial of f with respect to y at the origin. So this is the limit as k approaches 0 of f of 0, 0 plus k minus f of 0, 0, all divided by k. And so this is the limit as k approaches 0 of f of 0k minus 0 over k. So this is the limit as k approaches 0 of, plugging in 0, k, I get 0 times k over 0 squared plus k squared. But again, this is just 0 minus 0. So this is the limit as k approaches 0 of, well, 0 over k. And so the limit, so the partial. So I've shown that both partial derivatives exist and they're equal to 0. Now let's look at the limit as x goes to 0 of f of x kx. And let's just say that k is not 0. Okay. So this is equal to I want my screen back. Thank you. Okay. So this is equal to the limit. I want my screen back. Please come back to me. Okay. Okay, so this is equal to sorry, 1 second. Okay. The limit as x approaches 0 of f of x, well, that's just going to be x, y over x squared plus y squared. So this is the limit as x approaches 0 of x squared times, let's just write it as kx squared of k x squared over, factor out of x squared, so it'll be x squared 1 plus k squared. The x squares cancel. So this is the limit as x approaches 0 of k over 1 plus k squared. Well, obviously, this is a constant, and so it's just k over one plus k squared. And so that says that this limit does not exist. And that's what I wanted to show. And so I've shown that that limit does not exist. Okay. Let me do the following. Show that f sub x, f sub y are continuous everywhere. And so f is C1, yet f of xy at the origin is not equal to f of y x at the origin. Okay. So first off, well, this function here is a polynomial. So it's going to be, it's a rational function. So it'll be continuous everywhere except possibly where you divide by 0. And so I really have to only show that this is continuous at the origin. Okay, so f is continuous. everywhere except possibly at the origin. So let's see what happens at the origin. So let's look at the limit as xy goes to the origin. Of this. Okay, well, actually I should just say f of xy first. So let's look at this. Well, since we're approaching the origin, then we're not at the origin. So f is just defined as x cubed y minus x y cubed over x squared plus y squared. And let's just look at polar coordinates. So let's change this into polar coordinates. And so this is the limit, it's r goes to 0, of r cosine theta y r sine theta minus x r cosine theta y r sine theta cubed over r squared cosine squared theta plus r squared sine squared theta. And so this is equal to limit as r approaches 0 of, this will be an r to the 4th cosine cubed theta sine theta minus r to the 4th cosine theta sine cubed theta over, well, I can factor out maybe an r squared so let's factor out r to the 4th from the numerator. So I get cosine cubed. Obviously, I could factor out also a cosine sine term, but I don't really care about that at this moment. Minus cosine theta sine cubed theta. And cosine squared plus sine squared is 1. So I can cancel out 2 of these. And so I get the limit as r approaches 0 of r squared times stuff. Cosine cubed sine minus cosine theta sine cubed theta. This is bounded, and so it's something bounded times something going to 0 approaches 0. So this is equal to 0, which is equal to f at the origin. So therefore, f is continuous at the origin, And so therefore, f is continuous everywhere. Okay, good. Let's look at the partial of f with respect to x. Okay. Well, I know that the partial of f with respect to x, the derivative of a rational function will still be rational function. So again, this will be continuous everywhere except possibly at the origin. And so maybe I should say that. So f is continuous on everything except possibly at the origin. And while I'm here, I might as well state that for the other one. And this is continuous everywhere except possibly at the origin. So I really only have to check if the partials are continuous at the origin. Okay, so let's look at the partial at the partial of f with respect to x at 0y. So this will equal the limit as h approaches 0 of f of 0 plus h. Y minus f of 0y over h. Here I'm assuming that that y is not 0. Maybe I should state that initially. For y not equal to 0, let's compute start for y not equal to 0. Let's compute the partial of f with respect to x at 0y. So this is the limit as h approaches 0, f of 0 plus hy minus f of 0y over h. So this is equal to the limit as h approaches 0 of plugging in h. This will be h cubed y minus h y cubed over h squared plus y squared minus plugging in for x 0, 0 cubed y minus 0 y cubed over 0 squared plus y squared. Okay, so this is equal to limit as h approaches 0 of, let's factor out h from this, what remains is squared y minus y cubed over h squared plus y squared. This term here is just 0, so I'm subtracting 0, so I can just disregard this. Dividing by h, the same as multiplying by 1 over h. The h's cancel, and so I get limit as h approaches 0 of minus y. So as h goes to 0, well, this term goes to 0, so is this term. So I get a negative y cubed over, oops, I'm letting h go to 0. So this is a negative y cubed over y squared. And so I get a negative y. Okay, now let's do this at the origin. So I've done this when y is not 0. Let's see what happens when y is 0. Okay, so let's take the partial of f with respect to x, and let's do this at the origin. So this is the limit as h approaches 0, f of 0 plus h, 0 minus f of 0, 0 divided by h. So this is equal to limit as, not the limit, the limit as h approaches 0 of h, so that's x cubed times 0 minus h 0 cubed over h squared plus 0 squared minus f of 0, 0 is 0 over h. Well, 0 minus 0 is 0 over h is 0. So I'm just taking the limit as h goes to 0 of 0 over h. And of course, that's going to be 0. And so that implies that the partial of f with respect to x is minus y. For all y. Okay. And so let's do the same thing for y. So let's do the partial. Again, let me assume that x is not 0. And let's do the same corresponding thing. And so let's take the partial of f with respect to y at x 0. So this is the limit as k approaches 0 of f of x 0 plus k minus f of x0 over k. So this is equal to the limit as k approaches 0 of x cubed y, which is k, minus x y cubed, which is k, over x squared plus y squared, so k squared, minus plug in 0. So x cubed 0 minus x 0 cubed over x squared plus 0 squared, all divided by k. And so this is equal to limit as k approaches 0, factor out of k times x cubed minus k cubed over x squared plus k squared. This last term is 0, so you're subtracting 0 in the numerator. So we can just get rid of that. Times, well, the reciprocal. The k's cancel. So you get the limit as k goes to 0 of x cubed minus k cubed over x squared plus k squared. Well, k is going to 0, so these last terms go to 0. So it's just x cubed over x squared which is x. Okay, so let's do this at the origin also. So I don't know what happens when y is 0. So let's, when x is 0. So let's figure out what happens when x is 0. So let's take the partial of f with respect to x at the origin. So the limit here as x h goes to 0 of 0 plus h, 0 minus f of 0, 0 over h. So this is equal to the limit as h approaches 0 of plug in h0. So you get h0 minus h0 over h0. At the origin, this is just 0 over h. And so this first term is 0, my second term 0. So you just get 0. And as h goes to 0, 0 still remains 0. And so even when the x is 0, this still has the same form. And so the partial of f with respect to x So the partial of f with respect to x of, no, with respect to y. I'm sorry, I'm doing this with respect to y. Okay, so that was an error. Already did that. So the partial with respect to y at the origin. The partial with respect to y at the origin. Let me put a break in here so I know where to edit this video. Start. Now let's determine the partial of f with respect to y at the origin. So this is the limit. A goes to 0 of f of 0k, 0 plus k, minus f of 0, 0 over k. And so this is the limit as k approaches 0. Plugging in 0k, I get 0 cubed k minus 0 k cubed over 0 squared plus k squared. F at 0, 0 is 0, all divided by k. And so this first term is just 0 minus 0 over k. Well, 0 divided by k is just 0. As k goes to 0, 0 just remains 0. And so this formula is going to be true for x equaling 0 also. And so I can say the partial of f with respect to y at x0 is equal to 0 for all x. So now I've shown that this is true for all x. Oops, is for all x. Okay, good. Okay. So now let's look at let's see where where I am in this proof. Okay. Okay, so show that these are continuous everywhere. Okay, so let's look at so I've shown just these. Let me look at this term now. Let's look at when I'm not at the origin. Let's take the partials. So suppose that x squared plus y squared is not 0. Let's look at the partials. So if I'm away from the origin, I can just take the normal partial. So it's the derivative of the numerator. Derivative of x cubed y is just 3x squared y minus derivative of x y cubed is just y cubed times the denominator, x squared plus y squared, minus the numerator, x cubed y minus xy cubed times the derivative of the denominator, which is 2x, all divided by the denominator squared. Okay, so this is equal to, let's simplify this. So this is squared plus y squared squared. So 3x to the fourth y minus plus 3x squared y cubed minus x squared y cubed minus y to the fifth, multiply negative 2x inside the parentheses, minus 2x to the fourth y, minus and minus is a plus, 2x squared y cubed. Okay, so this is equal to, let's combine like terms, x to the fourth y, so 3x to the fourth y minus 2x to the fourth y is 1x to the fourth y. 3x squared y cubed minus x squared y cubed is 2x cubed y2 plus another 2x cubed. The x squared y cubed is 4x cubed x squared y cubed. I have a y to the fifth term and nothing else. Okay, good. Okay, let's look at, so I can show that this is continuous. So this is going to be a rational function. So it's continuous everywhere, except possibly at the origin. So it's continuous. So f is continuous. Everywhere except possibly at the origin. So the only real bad point here is the origin. So let's see what happens at the origin. And so let's take the, let's replace, so let's look at the limit as xy goes to 0, 0 of this partial derivative. And let's see what happens. I want to show that that's nice and well, that's just going to equal the same as plugging in 0, 0. which would be 0. Okay, so let's show that this is nice and continuous at the origin. Well, this is the same as the limit as r goes to 0 of r to the 4th cosine theta r sine theta plus 4 r squared 4 r squared cosine squared r cubed sine cubed theta minus r to the 5th sine to the 5th theta over x squared plus y squared, which is r squared squared. So this is the limit as r goes to 0 of, I can factor out an r to the 5th from this numerator. What remains is cosine to the 4th sine theta plus 4 cosine squared sine cubed minus sine to the 5th, all divided by r to the 4th. And so 4 of those r's will cancel. And so you just get the limit as r approaches 0 of r times something that's bounded. Cosine to the 4th theta sine theta 4 cosine squared theta sine cubed theta minus sine to the 5th theta, which is 0. Okay. And, well, we already showed that this was 0. So the partial is continuous everywhere. So now let's look at the partial with respect to y. Okay, so let's look at the partial with respect to y. Okay, and so if I do that, this is equal to and again, I'm assuming that x squared plus y squared is not 0. So this is equal to derivative of the first, so it's x cubed y minus, this was an xy cubed, so it's a 3xy squared times the denominator minus the numerator x cubed y minus xy cubed times the derivative of the denominator 2y, all divided by the denominator, x squared plus y squared squared. So this is equal to, let's multiply this out. So this is x to the fifth plus x cubed y squared minus 3x cubed y squared minus 3xy to the fourth. Let's multiply the negative 2y inside the parentheses. So it's a negative 2x cubed y squared. Minus and minus become a plus 2x y to the fourth divided by x squared plus y squared squared. And so this is equal to x to the fifth. X cubed y squared minus 3x cubed y squared minus another 2x cubed y squared, so that's minus 4x cubed y squared. And then 2xy to the fourth minus 3xy to the fourth is minus xy to the fourth divided by x squared plus y squared squared. So this is continuous. Everywhere except possibly at the origin. Okay, so let's show that this is continuous at the origin. So I guess I'll use the same sort of trick. So let's look at the limit. I want to show that this limit here goes to 0. Partial of f with respect to y. So this will equal the limit as r goes to 0 of, so now let's replace x by r cosine theta r and y by r squared by r minus r cosine theta r to the fourth sine to the fourth theta. All divided by r squared, well, cosine squared plus sine squared is 1, so x squared plus y squared. So this is equal to limit as r goes to 0 of factor out r to the fifth. R to the fifth, cosine to the fifth, theta minus 4 cosine cubed theta sine squared theta minus cosine theta sine to the fourth theta divided by r to the fourth. So 4 of these cancel. You can just get r. So this is the limit as r goes to 0. R cosine 5 to the fifth theta 4 cosine cubed theta sine squared theta minus cosine theta sine to the fourth theta. And as r goes to 0, this just goes to 0. Since you have something going to 0 times something that is bounded. Okay. And so the partial of f vector y is continuous everywhere. Okay, so now lastly, let's look at the partial of f with respect to x, y. No, let's do y then x. Partial of yx at the origin. So let's look at this. So this is the limit as k goes to 0 of the partial of f with respect to x. So f at 0 plus k, which partial with respect to 0 all over k. So this is equal to the limit as k goes to 0 of, well, we've shown that this is just equal to minus k, and that's 0. And so this is the limit as k approaches 0 of -1, which is -1. Let's do the partial of f with respect to x, y at the origin. So this is the limit as h approaches 0 of the partial of f with respect to y at 0 plus h, 0 minus 0, 0, all divided by h. So this is equal to the limit as h approaches 0, but I've shown the partial with respect to y at x, 0, is just x. And so this is just h. And therefore this is just 0 over h. And so I get the limit as h approaches 0 of h over h is 1. So this limit is 1. So therefore, I've shown that the partial, oops, don't want that the partial here are not equal, because one is 1, the other is -1. And that's what I wanted to show. So even though I have that the derivatives, even though the function is continuous and both of the partials continuous, I still have that the mixed partials are not equal. Okay, so